Welcome back. This video is going to be the only one that I make on the regression chapter. The reason for this is that I'm going to assume all of you have seen regression probably at least twice, maybe 3-4 times, and so therefore I don't want to go over all the fundamentals. So I'm going to assume you saw this as an undergrad. I'm going to assume you saw it again in the data science fundamentals class. If you took my machine learning class, you would have seen this yet again. So if that assumption is wrong, then what I would encourage you to do is watch my other videos. So these are videos that I've made over the years for the second course in statistics, as well as I use them in the machine learning class as well. And so what's really important about regression is, watch the simple linear regression video with the prediction intervals. Prediction intervals are important. Often that topic gets omitted. The model assumptions, the diagnostics, transformations, multiplicative models, and dummy variables will be the most relevant videos. So what I plan to do in this video is to cover whatever's new. Okay, so assuming you've had the basic, business statistics treatment of linear regression, what's different about time series analysis? So here's a quick summary of some of the things that are going to be different. One of our most important predictors is going to be the time period, t. So remember, t indexes our time period. And so we're going to be including that in the regression model to capture the trend component. Now we may be doing some additional transformations on it to capture, for example, seasonality. So we're going to learn about seasonal dummies, we're going to learn about Fourier terms. But this is going to be one thing that's quite different than what we've done with regression in the past. We're not going to talk about this now, but in the last week of the class, we're going to look at using a lagged version of y as a predictor in the model. This turns out to be a very powerful approach. It's kind of like differencing, but a little bit different. So we'll talk about that in the last week of class. Also in the last week of class, we're going to be covering how to bring decision variables into our regression models. So in a marketing role, the most important thing is going to be the marketing mix. So what the price is you're charging, how you're promoting the product. So whenever you make one of these policy changes to the marketing mix, what does that imply for some outcome variable like sales? And then also in the last week, we're going to be talking about how we can bring other control variables into the model. So our main focus is going to be really just on this first bullet during this video, but then just kind of hinting that there's going to be way more to come. All right. I want to talk about assumptions. And so in my videos last week, I emphasized the importance of looking at residuals. Let me just kind of state some of the most important results. So remember I said that one of the big differences between time series analysis and basic regression models is that we don't assume uncorrelated errors. So the errors could well be correlated. When that is the case, there are a couple really important implications to know about. So first off, I'm going to go to the second bullet. The OLS estimates that you would get from normal regression are still unbiased, but they're not blue. So what do I mean by this? So go back to my videos on basic, OLS theory and multivariate OLS theory, where I prove that OLS estimates are unbiased. And what you're going to see in that video is that when I prove unbiasedness, so when I prove that OLS estimates of the slope are unbiased, I never use the assumption that the errors are uncorrelated. Okay, so because I don't need that assumption, OLS estimates being unbiased will follow even if they are uncorrelated, because I haven't had to use that. Now, another thing that I talked about in those two videos was the blueness of OLS. Okay, so blue, remember, stands for the best linear unbiased estimator. What this really means is that among the class of all, unbiased estimators, so the U part, so if we only look at unbiased estimators, the OLS estimates are the best in that they have the smallest variance. So they're going to be the most reliable estimator that you can get among all unbiased estimators. Now, when you go back to the videos that I showed, that I referenced on the theory, what you're going to see is the variance, computing the variance of OLS estimates actually does invoke the uncorrelated error assumption. And so what I never proved blueness because it's far more difficult for than we can tackle in that basic class. But it turns out that you can do better than OLS in terms of the variance of an estimator if your errors are uncorrelated. So a lot of textbooks on time series will have a module on weighted least squares and related methods that can allow you to improve the efficiency of your OLS estimators. So just know that, that's kind of important. So OLS estimates in the presence of correlated errors are still unbiased, but a big problem is they're not blue. Now, because of the correlations between the errors, in addition to affecting the kind of the overall variance of your estimates, the variance estimates of the individual parameters will also be wrong. And so the basic formulas that are given in the first class that in turn get used in computing confidence intervals and doing hypothesis tests are not right. And therefore, never trust a confidence interval or a hypothesis test when you've got correlated errors. So the standard errors need to get estimated a different way, and we're not going to talk much about that in this class. We'll talk about some of it in the last week, but that's kind of another top-level finding that you need to be aware of. Don't trust a confidence interval or hypothesis test, and don't trust anything about the variance in the presence of correlated errors. Finally, when we do have correlated errors, I've alluded to this in previous videos, there's additional information in those autocorrelations that can be used to improve forecasts beyond what we're doing with just regression models. So in using just a basic regression model, we're missing an opportunity to harness those autocorrelations to improve our estimates. All right, what do we do when we have autocorrelations? Well, we're not going to do much with this week. All I can do is promise a more thorough treatment later on in the course. We're going to be taking differences. We saw how that worked in some videos last module, where the differencing got rid of these autocorrelations and reduced things to a white noise process, and then our life was easy. We're going to find that we can also get rid of them by adding predictors to the model. And that'll come in the last week of class. So let's kind of put off this topic until the last week of class. Finally, in this introductory slide, I just want to say that we're going to want to use regression whenever there are other predictors that we want to be including in the model. So that's the strength of this approach, as opposed to some of the other methods that we're going to cover, like exponential smoothing or ARIMA, where we really can't be including other predictors in those models. All right, so let's now do a deep dive. Think of this slide as a deep dive into this first bullet. So if we want to use regression to model time series data, we will start by applying some variance stabilizing transformation to y. So as I taught in the previous module, you can use Box-Cox, You can take a log or square root as a special case of Box-Cox, but you want to stabilize the variance. We may be doing some differencing if necessary. So these are just some pre-processing steps that we covered last week, and I'm going to assume we're going to keep doing that before we build a regression model. Now, having done these pre-processing steps, what I'm going to focus on this week is how do we capture trends and seasonality. So that's really the focus of this video, is capturing trends and seasonality. So here's an example of a model that we would use if we had just a linear trend. So it looks like a simple linear regression model. The only difference is that with simple linear regression, we would usually call that x. Here we're putting in t as the time trend. And so the basic idea of this model, let's go over my document camera for a second, is this. Instead of putting an x here, we're going to put a t here. This is my y variable, so the outcome variable. And this is just the simple linear regression model that you know and love from your previous classes. So the slope is beta 1, your intercept is beta 0, and we're capturing that trend through using the slope and intercept. Now, we could make this more complicated with a quadratic trend. So a quadratic trend could be something like this, where we have part of a parabola. And so the equation of this is y equal to beta 0 plus beta 1t plus beta 2t squared. And so if you suspect you've got a quadratic trend, one way to deal with that would be to fit a regression model by adding a quadratic term to t. Now, we talked about multiplicative models, and so really what that is an exponential trend model. So if we have an exponential trend, what we'll end up doing is just logging both sides, or maybe we use a Box-Cox transformation. But the point being, we can log both sides to capture an exponential trend, and that would be even stronger than a quadratic, growing even more quickly than a quadratic. Another technique that gets covered in the regression chapter is to, I'm going to say, go non-parametric. So my first three models capture a trend using a parametric function. So a line, a parabola, or some exponential function. Alternatively, we could use, so the book talks about a cubic natural spline or piecewise linear splines. I'm not going to cover those because they've been covered in a lot of detail in my machine learning class. So that stuff back in machine learning is very fundamental, and you can watch my piecewise linear lecture or my cubic lecture by clicking on those. Okay, so that's about all I want to say about capturing trends with regression models. What about seasonality? So the most obvious way to capture seasonality when you have time series data is simply to make the season or the cycle, so cycle variable in R, make it a factor. And so when you make it a factor in a linear regression model, R will create dummies for you. So for example, if you have quarterly data, you will get 3 dummies, of course. If you have monthly data, you'll get 11 dummies. One comment about this approach is that if you only have quarterly data, it's hard to do much better than quarterly dummies. So you're burning 3 degrees of freedom by including dummies, and that's fine. However, when you have more periods in a cycle, so for example, months, or it could be hourly data. If I'm looking at weblog data and I have measures of the visits that I have for every hour in a 24-hour clock. So then I would need 23 dummies. With monthly data, I would need 11 dummies. And you're burning through a lot of degrees of freedom. So what we'd like to have is a more parsimonious way to capture the seasonal aspects without burning so many degrees of freedom. One of the most important ways to do this is using Fourier series. So Fourier series is a very important area of analysis and mathematics. Fourier series is used throughout engineering and physics whenever you have some sort of a periodic function. All right, and so there's a very important result, and it's kind of summarized in the first paragraph here. And it simply says this: with appropriate weights, we can get to any function as close as we want with one of these Fourier transforms. And if the function itself is periodic, which is really what we have with seasonality, you can do it for the entire range of the function, the domain of the function. Let's call it the domain. So anyway, what is a Fourier series? So Fourier series uses the sine and cosine function to represent a periodic function. So the way you should be thinking about this is it's kind of like using a log transform or an exponential transform or a squared transform. It's just that we're using the sine and the cosine functions to capture the periodicities. So recall what a sine wave looks like. So a sine wave looks like this, and it keeps going up and down. I ran out of paper here. This is a very natural way to capture a periodic seasonal effect. Now, if we add this to a cosine function, so here's your cosine function. When you take a linear combination of the sine and cosine function, you can represent a broader class of periodic functions. There are ways of increasing the frequency, so to make sure the sine wave has a shorter period. So if you do that, you can represent even more types of seasonal patterns. All right, so the upshot is R does this for you with a Fourier function. And so think of the Fourier function as being kind of like the log function. It goes off and it computes these transformations for you and includes them in the model. Now Fourier also includes an additional argument, kind of like the degrees of freedom argument that we had with splines, to let you control how flexible that series is going to be. So I'm going to do an example of this in a second, but those are kind of the big ideas. If you want to capture a seasonal effect without burning a lot of degrees of freedom, use these Fourier terms. One more point. This is an extremely deep and rich topic within time series. There's a different approach to time series that gets covered in a lot of textbooks, not really in our textbook, called the spectral approach to time series, that really develops this further, but we're not going to use that here. Finally, I just want to mention one other function that's useful. R includes a function that creates dummy variables for when Easter occurs. So Easter is a very kind of problematic holiday because it moves around every year. And so when Easter happens, certain goods will spike. There'll be a demand spike around Easter. And so you want to be able to capture that, and the Easter function does that. So since it occurs different times every year, It's really nice to have a function that keeps track of that. Now I want to talk about some special functions in the forecast library for using linear regression to fit time series models. So there is a function called TSLM, which is a special version of LM built for time series objects. So in particular, TSLM allows for two special variables. So it creates these on the fly for you. So one is the trend variable and the other is the season variable. So the way to think about trend is it's just my little t, it's time. It's this what I was talking about right here. So if I want a linear trend model, I would just regress my y on the trend. Season is going to create dummies for us. It's going to create a factor variable that will have quarter 1, quarter 2, quarter 3, quarter 4, and make those into dummies for us. So those are very convenient ways of doing exactly what I said on the previous slide. Another thing that TSLM does that LM doesn't do is it will compute the Box-Cox transformation for you and then undo it on the back end. And if you want, it will even use the Box-Cox.lambda function to choose the optimal lambda for keeping seasonality constant. That's the variance of seasonality constant. So another useful feature of this. There's also some additional functions that can be used with objects of class TSLM that are returned by this function. So fitted values are returned with the fitted function, residuals with the residual function, and you can make forecasts with the forecast function. So let's look at an example. Remember the Amazon data set looked pretty linear after a Box-Cox transformation, or for that matter, a log transformation. So let's go take a transformation of Amazon and use the TSLM to model it. So this is the call that I'm going to make. So a couple things to notice about this is I pass Amazon to it, then I'm giving it a formula, so tilde. I want the trend and the seasonality. I don't need to specify the data frame. So what R is going to do is just take a look at this TS object Amazon and then create trend and season from that time series object. I'm going to give it the lambda that I computed with Box-Cox.lambda, which you'll see is about 0.17. We found that in a previous video. Alternatively, I could have just said lambda equals auto, and it would have I wouldn't have had to do the previous command. All right, what do I get when I display one of these objects? Well, you'll see I get an intercept and a slope plus 3 dummies for my second, third, and fourth quarters. The first quarter is the base category. Just for fun, maybe I want to do a log model instead. So if I want a log model, remember I can set lambda to 0 for the Box-Cox transformation, and that's the equivalent of just taking the log. And so you'll see I get something pretty similar. Notice the basic story is the same. The units of the dependent variable have changed. We've gone from whatever this is, something a little bit not quite as strong as a log, to a log. And as a consequence, the magnitude of the coefficients has changed a little bit, but the basic pattern is the same. So fourth quarter is very good. You're going to see that it looks like the second quarter and the third quarter both have negative coefficients. The trend is positive in both cases. It's always a good idea to go check your residuals. Let's go just do the check residuals. What you're going to see here is we're going to test for 8 autocorrelations, the first 8 autocorrelations. The p-value is tiny, so we're going to reject the null hypothesis that the first 8 autocorrelations are all 0. My basic conclusion is There are pretty strong autocorrelations in that data. All right, well, let's go look at our plots. So I've used the auto plot with the auto layer function to compare these two fits, the box Cox versus the log. And so all this is shown on the next page. So let's start with the residual plot. The residual plot is not looking good. So what we see is all the residuals are positive for a while, then they're all negative for a while, then they're positive again. And so this is very common when you've got cyclical behavior that you're not modeling. And we've made no effort to capture the cyclical part of this. The ACF is reflecting that. So what we see is at least the first 4 or 5 autocorrelations are significant. So we've got a lot of work to be done to capture that. Finally, let's go look at what I've created with the layer plot. And so what you'll see is the blue line is for the log function, the red is for the box Cox, the black is the original data. And the two transformations are pretty similar until we get towards the end of the data where they diverge, and looks like logs are overestimating things, the box Cox is underestimating things. One thing to note about this is notice TSLM has transferred everything back to the original scale. So these are not on log scale or box Cox scale. These are on the original scale. So it's transformed things back for us. I'd like to do one more part of this example. So let's suppose I want to create forecasts into the future for the Amazon data set. So for this example, I could have used the functions that I fit before, but I'm going to log it myself, which is going to put things on a log scale. Remember, if I use the lambda argument out here, TSLM will convert to a log scale, then it will convert back. I just felt like putting everything on a log scale for now. So we see pretty similar coefficients that we had before. In fact, these should be identical to what we had before. To make a forecast, remember I said there was a forecast command. With LM, we would use predict. With TSLM, we're going to use this forecast command. And here I'm saying, give me an additional 4 quarters of predictions. And so if I do this, you're going to see I get my point estimates from the TSLM function, just dropping those, going off into the future. We get the predictions, as well as the 80 and the 95% prediction intervals. I've created another plot for us showing the predicted values along with the prediction intervals. So by default, you get those. I also extended it to 3 years just so we could see the predictions for a little bit longer. So despite the fact that we haven't made any effort to account for the cyclical part of this, this forecast seems like it's pretty good. I'm fairly happy with this. So these new functions that we have for using basic regression are going to be very helpful. I'd like to do another example with you now, which illustrates the Fourier transform. I've got another data set, which is the employment, number of people who are employed each month. So this is monthly data. We're going to need, we would need 11 dummies in order to have dummies on this. So what you're going to see is I first fit it with just trend and season here. So we're getting the trend and then 11 dummies. This is going to give us a total of 13 degrees of freedom. So 11 dummies plus a trend plus an intercept. Or instead of using season, I could say Fourier, employment, and then I give it an argument kind of like the degrees of freedom argument that tells how many Fourier terms. So if I say k equal to 1, I'm going to get a sine term and a cosine term. And so when I go down and look at this fitted value, what you're going to see is this is actually the sine term. That S means sine, and the C means cosine. So when I say k equal to 1, I'm really adding 2 degrees of freedom to this model. This would have a total of 4 degrees of freedom because it would have the slope, the intercept, and then the sine and cosine terms. If I say k equal to 2, then I'm going to get 2 cosine terms. So the second cosine term would have higher frequency, and likewise with the cosine term, for a total of 6 degrees of freedom. K equal to 3 would get me to 8 degrees of freedom. And notice all of these are substantially less than the 13 degrees of freedom that I would need if I'm using dummies. So I've used the autoplot command just to show a variety of these. And so it looks a whole lot like the smoothers that we've seen in the machine learning class. So what's happening is the green line is going to be the smoothest of them. So you'll see that it does the kind of the weakest job of capturing the peaks of this seasonal time series. As I start increasing my degrees of freedom, the fits get more and more flexible, and they get closer and closer to the version with the dummies, which would be a very flexible version. This is another way to it's control the bias variance trade-off. Just increase the number of terms, and the function gets more flexible.